Hi all. So in this video, we'll be seeing about the VLSI flow, VLSI and the ASIC flow. So the very first step in case of the VLSI flow is to gather the requirements, based on the market survey or the user survey. So we kind of get what is the requirements or what is the actual things needed, which is from the user point of view, right? And so So initial point is the market survey or the user feedback kind of information. So once we get a market survey, so based on this, we'll kind of create a spec which kind of captures all the requirements in a very clear manner, right? And all the dependencies and all these things are mentioned in a formal document called as the specification or the spec. So once we have the spec, we kind of go for the block diagram, right? Yeah, the block diagram, or we can see it as the microarchitecture. Go for the microarchitecture, where we have a very high level block diagram of the entire, let's say SOC or whichever application you're actually designing this particular flow for. So once we have these block diagrams, we kind of go for the multiple blocks which are there inside, which needs to be there, and how they need to be connected, right? So this kind of microarchitectural design we come up with. So once we have this block diagram or the microarchitecture, then we go for the individual block level, right? This there will be different owners. So this is block is owned by a particular team, and this is owned by a particular team. So each of these individual owners then come up with some microarchitecture or block level diagram for this. Right? So once we have the individual block diagram, then this kind of becomes the golden thing for them. So then we have the RTL design. Yeah, so RTL design is basically convert this microarchitecture. You'll have a lot of block diagrams and FSMs and uh, those kind of info. Those needs to be converted into a meaningful form, which is in the form of a coding language, which we use most commonly use are the Verilog system Verilog. And in some places, we also make use of the VHDL as the programming language. So this is a very high level description language which kind of concisely puts all the info which is given in the micro architecture or the block diagram stage. So once you have the RTL design, so whatever RTL designs, we need to check for some basic quality checks in the form of linting quality checks. And we have the clock domain crossing checks within the block. So let us say the individual initially what happens is we have a particular blocks, say audio or video, right? So we are just trying to design this particular block. So each of these blocks needs to design their own blocks first, and then once all these blocks are done, then we go for integrating all these blocks into a complete chip. So we are now talking with respect to one particular block. So we design the block and then do the quality checks, any kind of QA here. So here we do this linting, CDC, any kind of low power checks. Low power checks, and we kind of give the power intent, which kind of adds any kind of retention and isolation level shifter, these kind of power strategies into the design. So once this is done, then we give this to the design verification team or the DV team. So who kind of checks the design with respect to the spec. So they compare the spec versus the design. If the both these are matching, or is there any violation coming from the spec. So they have their own no, different environment, something called the test bench, and the uh, a complete environment, which kind of checks against the spec, and if there is any issues against the any kind of protocol violation, or kind of it is violating something from the spec, or is there any bugs within the design. So that is actually comes into the design verification stage. So in case if there is any issue, so that kind of is communicated to the RTL designer. So in that case, the RTL designer has to uh, fix that bug, and then again give an incremental release for the not design, and the cycle again continue. The same goes on for the linting, right? So if there is any issues with the linting, we again go back to the RTL designer and say there are some linting issues and CD0 project issues. So these get cleaned up, and it comes back as an incremental release. So once everything is clear and all the quality checks are good, and all the no, there's no issues with respect to the design very stage. So then we move on to the next stage, right? Uh, where we kind of so each of these blocks. So let us say there will be an individual HM level block. So we kind of do the synth for that. We do the synthesis stage. So, and during the synthesis stage, this high-level language code, behavioral model code is converted into a gate-level netlist, and right. Also, we check for the timing closure here. Make sure that there's no timing violation here, and basically we set up for the setup violation here and not the hold violation here. Not the hold violation is not checked in case of the synthesis, as we do not have any kind of clock tree at this particular stage. We only have the data path here. So basic no basic any kind of to give an example of timing, we have like a reg to reg path. This is let's say this is a clock path. So we make sure that whatever info which is coming in data, and so whatever, and the time it reaches the next clock cycle, it is no, the water combo delay is less than the amount of time of the next clock cycle, and it reaches pretty much before this next clock cycle. So this is kind of what we check in the timing thing. We're not going too much deep into this, as this is more of an overview video here. So this is what exactly happens in a synthesis, and also what happens is and so far what this actually gets mapped to the actual technology libraries. So we also give the in one of the input is the library files here. uh, so we give the tech library files, and so these actually get mapped to those technology library files. So those comes from companies like TSMC and Global Foundry, so on. So this is where actually the chip gets manufactured. So we get the libraries from there and give it as an input to the synthesis, and much of the stages downwards as well. So these are the three things which happens in this. One is conversion of the complete design into a gate level netlist, and then we do the timing closure. Mainly the setup violation is closed, any setup checks are closed, and then also we map all these different gates and cells to the technology library cells. So this actually forms the front end part of the LSI flow, right? Right from the spec or the RTL design to the synthesis stage. This is synthesis somewhere in between the front end and back end. So once this is done, we also have the DFT stage, right? This is designed for testability. So once you have manufactured, you'll not be able to add anything into that. So we kind of keep some tests related logic as well into the design, so that it becomes easier during the time of post silicon validation. This becomes much easier. So this kind of alternative steps, right? There can be DFT done, and then once again, once the DFT is done, we kind of do the synthesis with that as well. So yeah, this kind of DFT can come before this, and then the synth here. Once these two steps are completed, then we go into the complete backend flow, which is called the physical design step. So initial step is the floor plan here. Floor plan is where we design the actual, the shape of the chip. How should it be, like a square or a rectangle? We have some parameters like aspect ratio and the height is to width, and based on that we come up with the actual shape of the uh, chip, and we then place some of the macros here, like memories and all this kind of plays in the initial floor planning stage itself. Then we have the floor placement stage. So in during the placement stage is where we keep all the design cells, actual design functional cells are actually placed into the chip. And then we have the clock tree synthesis here. So clock tree synthesis is where we give the complete clock path, right? So if before this we do not have the any kind of clock to any of these logics. So here all the clocks is fanned out to all the logics within the chips. This is the stage of clock tree synthesis. And we have something like routing. So routing is the stage where we actually have the wires for all the data paths. So whatever we saw here, these wires are not there initially. Wire delay is not there, but in case of routing only, we see that all these routing delays, everything comes into picture. Also, we have as in at a similar parallel step, we have the power rails, right? Power rails, all these being led. So we have like different power rails, like just kind of given as a mesh structure, and with this, we have it as like VDD here and VSS from the other stage, and so this power kind of gets goes to each of these cells, right? So this kind of avoids a lot of leakage as we kind of have a mesh structure here. Once we're done with this, then we go for the again timing checks with respect to STA, which is called the static timing analysis here. Here we have both the setup and hold checks. As we have done already the clock trees and this is, so we kind of check both the setup and hold check here. So once this is timing closure is closed, we go for all these the analog layout or the custom layout step, analog or custom and memory layout steps. So and based on this, we get a complete blueprint or the GTS2 file here. So once we are done with the layout stage, we get a blueprint or a GTS2 file. So which then goes to the foundries which I mentioned earlier. Foundries like the TSMCs, Global Foundry, etc. And then this kind of gets the chip gets manufactured from these chips. So we kind of book a slot here and get the chip manufactured. So once the chip is manufactured, we do again something called the post silicon validation. So yeah, this is basically the flow of the entire VLSI flow. Thank you.